So today is practical group theory day. Which means that Jenny won't recognize it. But these are the techniques that I use. I mean, basically, the goals here are learning to write invariant Lagrangians, reading out the properties of the invariances, and having a compact notation that allows us to focus on what's important. So that's the main thing. I don't think I'll review the properties of groups, but let me just comment about SUN groups. So SUN groups are the ones that we're going to end up using a lot, and they have representations that can be taken to be n by n unitary matrices with determinant equals 1. And so that's the unitary part is why they're so nice in physics. The n by n just means that they're invariances of n objects. And the determinant equals 1, we'll see what that comes by doing a practical example. But for any unitary matrix, you can write that as e to the I times a Hermitian matrix. And by our identity that we've been using, determinant of this matrix is e to the trace log u, is then e to the trace h, so that h is traceless. If determinant of u is 1. So if we count the parameters, so h is an n by n, so n by n Hermitian has n squared parameters. The trace is n squared minus 1, and the diagonal elements, you can make n minus 1 of those be diagonal. So that's the basic counting. Nothing fancy there. Okay. We're going to do invariances of 2 objects. First. So let's imagine we have 2 fields. Psi is psi 1 and psi 2. What invariances are possible? Well, clearly the invariances would be psi goes to psi prime, which is u psi, with u dagger u equals 1. So that's an invariance. Well, it will leave, in this case, it will leave the Lagrangian unchanged. Okay. So in the cases, these are meant as fermions, so we always end up taking matrix elements of psi dagger psi. So whenever there's these 2 fields, that then goes to psi prime dagger is psi prime, which is psi dagger psi. Okay. So, but basically the point is that if the rest of the Lagrangian cooperates, then a unitary transformation can leave the Lagrangian invariant. Okay. Yes.
Could it be more general than that? In other words, it could leave the Lagrangian the same up to a constant or up to a surface term?
Yeah. I can't think of a way to do that for just a simple rotation for given 2 fields. You know, Yes, the answer is yes. You could do that, and there certainly are things like translation symmetries that you can do that with, where you translate it and then you get something that's a total derivative.
So as long as at least the equations of motion is the same.
Yeah, I mean, in the end, the full condition is that you have to leave the path integral the same. Okay, we'll see that there are some transformations that leave the Lagrangian the same, but change the path integral measure. So those are a separate category of stuff. So that's in the end the ultimate thing. But if the path integral measure is fine and the Lagrangian shifts by a surface term, then the action is unchanged, and so then you're fine. Okay, so at this stage we have unitary 2x2 matrices, which you can write as U is e to the I alpha times the identity matrix. I guess I'd like to put a minus sign there, plus alpha vector dot tau Okay, so this first one generates an overall U1 invariance. The second one is going to be the SU2 piece, and the tau here I are going to be the Pauli matrices. Okay, which are often called sigma I, but we'll call them tau I just to keep them distinct. So they're traced as 2x2s. Okay, so this then separates out a U1 invariance and an SU2 invariance, and so we can have either type of invariance, but the SU2 can be distinct from the U1. They commute, so there's no reason that you're forced to keep them together. Okay, some things about the Pauli matrices, as you know, so tau I, tau j, 2I, epsilon I, j, k, tau k, that's the usual one. We'll take the usual normalization being tau I, tau j is 2 delta ij. Tau I, tau j itself is the matrix 1 times delta ij plus I epsilon I j k tau k. And then the one that those you've probably all seen. The one that's useful for what I'm about to do is tau I, the AB matrix element of that, tau I, the CD matrix element of that. Okay, so these are 2x2, so A and B run over 1 and 2. The i's are summed over here is 2 delta AD delta BC minus 1/2 delta AB delta CD. Okay? How many folks have seen that identity before? No? All right, so let's play with it a little bit. It's actually a very, very useful identity. And it plays a role in what we're doing now. So let's just do some checks on it. If I take another tau, let's call it tau j, well, actually, let me do the following first. Let's do the following. Let's first take delta A B on this thing. So tau I A B, tau I C D. Okay, that on this side of the equation, you know that it has to be equal to 0 because they're traceless. So on the second side, the other side, there is 2. If I sum over delta A B on that, that first term becomes delta C D minus 1/2 times 2 delta C D equals 0. Okay, if I take tau I A B, tau I B A, so I set delta B and C equal to each other and D and A equals to each other. That's trace tau I by the definition of trace, which each of the i's gives 2, so that should give me 6. And on the other side, it's 2 A and B equal each other, C and D equal to each other is 3 minus 1/2. No, I'm sorry. No, I did that wrong. It's A and D were equal to each other, so the delta AD times delta AD is 2 times 2, so that piece gives 2 for each of the delta functions, and then minus 1/2, this guy gives 2, because I've taken A and D equals to each other and B and C equals to each other, so this, when they're all 1, it gives 1, and when they're all 2, it gives another 1, it gives 2. Okay, so it ends up being 6 also. And the other one that I started also should work out. I actually don't have it written down here, so let's try it. Tau J A B, or let's make it I wanted B A tau A B I tau I C D is, that first one is 2 delta IJ tau I C D, so this should equal 2 tau J C D, and if I come over here and I put B A AB, so this piece here, delta AB on this, it gives 0 because that's a trace, and this gives yes, it does. It gives 2 tau J, then B is equal to C, and A is equal to D. Okay, so there's various ones. That's basically what you need to derive it, I think, is a set of things like that. You write out the most general formal on that side and require consistency with all these conditions. Okay, this will turn out to be important in what we're about to do. So anyone want to talk more about it? Okay, it's a useful identity. I'll give you the same one in SUN soon. Okay, so invariants. So if I have in a Lagrangian psi bar operator psi, if the operator is something is proportional to the 2 by 2 unit matrix, then that just turns into psi bar u dagger o u psi, which is psi bar o psi. So this leaves anything that has a unit matrix in it as a singlet. But what about something that looks like psi bar tau I psi? Okay, so that's not an invariant anymore. That turns into psi bar u dagger tau I u psi. U dagger tau I u is the 2 by 2 matrix. It's Hermitian. If you take the Hermitian conjugate of that, it comes back to itself. It's traceless. If I take the trace of that, the cyclic property of the trace gives me 0, lets me get that to be equal to 0. And so that's sufficient to say that this looks like some Rij tau j. Okay, so it has to be some linear combination of tau matrices. We can find Rij in the following way. Is if I take the trace of Rik tau k with tau j, and I take a factor of a half, that's Rij. Uppers and lowers don't mean anything. Sorry, I just wrote some down lower, but it doesn't matter upper or lower. Okay, so this tells me I can pick out this by taking 1/2 trace u dagger tau I u tau j. That's Rij. And remember, u has the form e to the I minus I alpha dot tau itself. But now I want to show that, I want to claim that Rij is an orthogonal 3 by 3 matrix. Which is that's a rotation matrix. So this is the group O3. And so what does that imply? So an orthogonal matrix Rij Rkj should equal delta Ik. So it's summed over J. That's the definition of an orthogonal matrix. Okay, so rotation matrices are examples of that. Okay, so let's look at what we have here. This is 1/2 trace u dagger tau I u tau j 1/2 trace U dagger tau K, U tau J. Okay. Now, at this stage, I'm going to write this as, this term here as U dagger tau I U B A tau J A B, and this one as U dagger tau K U D C tau J C D. So the trace is summing over the indices in that way. Then I go up to my identity, which sits up here, and aside from I going to J, it is that identity. Oops, it's not on the screen. There it is. Summed over J, A, B, C, D has that feature. So this then down here turns into 1/2 or 1/4 times 2 times, well, the first piece in that was A and D are the same and B and C are the same. So it becomes U dagger tau I U U dagger tau K. So it's B A B. And the second term was minus 1/2 was U dagger tau I U A B delta A B U dagger tau K U, it was DC delta CD. Okay, so these both turn into traces now, so summing over indices. These last ones here become trace of taus, which are 0. And this one equals then 1/2 times trace U dagger tau I U U dagger tau K, and there's a U sitting there, which the U's all disappear, and this becomes delta I K as advertised. So we've gotten out a O3 matrix out of an SU2 transformation. So this transforms like an O3 vector, which is, some VI goes to Rij Vj. If I take let's just do one example and you can see what comes out. If I take U is e to the minus I alpha tau z. Okay, so this is around the z-axis then. That implies Rij is, if you work it out, cosine 2 alpha sine 2 alpha minus sine 2 alpha cosine 2 alpha 0, 0, 1, 0, 0, 1. So it tells you that rotating U by an angle alpha rotates R by an angle theta, which is 2 alpha. So there's a twofold mapping of SU2 onto O3. If alpha is pi, Rij is equal to 1. If alpha is 2 pi, Rij equals 1. But but U's are not identical. It basically U turns U in one case is plus 1 and the other case is minus 1. So you've got this twofold mapping. But since R involves two U's, U going to minus U doesn't change it. Okay? So representations of SU2. Okay, we take the doublet, psi is psi 1, psi 2, with psi going to U psi. That's the fundamental representation. The vector, anything that transforms like, let's call it pi I, which will be pi 1, pi 2, pi 3, goes to Rij, pi j, that's the adjoint. Psi bar psi is the singlet. Psi bar, that's this. Tau I psi is a vector. And this is then the group theory that a doublet cross a doublet is a singlet plus a triplet, or in the old spin language would be 1/2 cross 1/2 is equal to 0 plus 1. So this is spin language. Okay. Okay, so our interest is in writing invariants. And so this is really the important thing. If we write out the Lagrangian is psi bar tau I psi pi I. So we summed over those indices. That's an invariant because this transforms into Rij psi bar tau j psi Rik pi k, but by the invariance properties that turns into delta jk. So this is then psi bar tau j psi pi j. And so all you have to do really is just write invariants with psi's, taus, and pi's. There's a notation that we're going to end up using. So let's make pi with no index on it is tau I times pi I. So this is then a 2 by 2 matrix. And this transforms as, this by itself, as a matrix. As pi goes to tau itself doesn't really transform, it's just a matrix, but it becomes Rij, tau I, Rij, pi j, which is 1/2 tau I trace of u dagger tau I u tau j pi j. But then I'm going to use our little favorite identity, and oops, let's see. Excuse me, I have to. This whole beast here then is tau I c d u dagger. No, I'm sorry. U tau j u dagger c d. Or DC. DC is the right order. Okay. This, I'm going to take the AB matrix element of that and use my identity. Okay. This then turns into, so tau I Rij pi j AB is then 1/2 times 2 delta AD delta BC minus 1/2 delta AB delta CD of times 2. I have u tau j u dagger dc pi j. Okay, the delta CD piece is a trace of this that disappears, so that piece doesn't contribute. This one, D becomes A, B becomes C, or C becomes B. So this then turns into u tau j pi j u dagger AB. Okay, so in matrix notation, yes?
Can you explain why the trace of u dagger is 2?
Yes, I'm sorry. Let's do that. So trace, first of all, any trace of AB is trace of BA. I'm going to use that property. So then if I take trace of u dagger tau I u, that's the trace of tau I u dagger. U dagger is 1, right? Okay? Yeah, sorry for not saying that out earlier. That's something I've been using repeatedly. Okay? So basically when you take the trace, these guys cancel and you're just taking the trace of what sits in the center. Okay? So in matrix notation then, this pi which is tau dot pi, goes to u pi u dagger, or u tau dot pi u dagger. So it just as a matrix, it transforms with u and u dagger sitting on the outside. So that then our invariants, you don't, this klutzy way that I was proving all these things here, that these things transform like Rij's, and those are orthogonal matrices, etc. All that becomes irrelevant. Once I have this, we then have the matrix notation for the invariants. If I have psi bar tau dot pi psi, that the proof then is easy. The way you'd prove it is that psi bar u dagger u tau dot pi u dagger u psi. Each of these is the transformation of their respective beast. That's then very obviously invariant. So the adjoint fields then, all the adjoints transform like, so tau dot any vector field in this thing goes to u tau dot vector field u dagger. Okay, it's easy to write out another invariant. This one is pretty obvious, but it's less obvious when you go to other groups. If I take 1/2 trace tau dot pi, okay, that's 1/2 trace tau I, tau j, pi j. The trace is 2 delta ij, so this is pi I, so it's summed over things. But that's an invariant because that transforms to 1/2 trace u tau dot pi u dagger u tau dot pi u dagger. So you can use this matrix notation. So then the u's disappear by properties of the traces. It's the same thing that we started with. Okay, so writing out these invariants allows us to know what the invariants are. It also lets us do group theory on our heads in a way. So let's do some calculations with it. Okay, so first let me write out what tau dot pi is here. Okay, I guess at this stage I'm going to assign, so let's assign charges so that I can keep track of things. Let's call psi being psi proton, psi neutron for the doublet. So there's two fields that carry different charges. Tau dot pi is tau 3 pi 3 plus tau 1 plus I tau 2 pi 1 minus I pi 2. I'm going to put factors of 2 in soon, plus tau 1 minus I tau 2 pi 1 plus I pi 2. And I've got too many of those latter ones, so I have to put a half out in front. Right? And we'll take tau plus is 1 half tau 1 plus I tau 2, and minus with a minus. Those then are the raising and lowering operators, and I'll define the fields. Pi plus is 1 over the square root of 2 pi 1 plus, it's actually the one, the way it works out best I think is pi 1 minus I pi 2, and pi minus is square root of 2 pi 1 plus I pi 2. Those are then the right charge states come out if I do that right. This implies then that the matrix tau dot pi is pi 3 minus pi 3 square root of 2 pi plus square root of 2 pi minus. Okay. Pi dot pi is then pi 3 plus 2 pi plus pi minus. So those are our beasts, and if I write out the Lagrangian is, I'm going to actually do, these are real nucleons and real pions. Excuse me if you're not completely clear what those are, but I'm looking mainly at the group theory properties, tau dot pi. I'm putting a gamma 5 in there because these are actually pseudoscalar fields, and that makes the parity right. But if you don't want to worry about that, don't. In fact, I'll just drop the gamma 5 for now. That's IG P bar N bar, this matrix pi 0 square root of 2 pi plus square root of 2 pi minus minus pi 0 Pn. This Lagrangian then contains the following. It's G P bar P pi 0 coupling minus P bar N bar N pi 0 plus the square root of 2 G P bar N pi plus the square root of 2 N bar P pi minus with a G. Okay. So this Lagrangian now, you can read off various couplings. Let's do it down here. In general, we'd write this vertex, something like P pi 0 as I G P pi 0 gamma 5. Okay, the gamma 5 I've now just stuck back in there. So for writing out Feynman rules, we write that out. We then see that G P pi 0 is G, G N pi 0 is minus G, G N P pi plus, is square root of 2g, and g p n pi minus is square root of 2g. So what's come out of this is some physical consequences that you might not have guessed. The relationship between all these coupling constants. There's 4 coupling constants. They're related. 2 of them you could have guessed easily. The other 2 with a little thought. If you were doing this using regular group theory, how would you do it? Well, you'd do it with Clebsch-Gordon coefficients. So the Clebsch-Gordon coefficients, if you look up what's the coupling of, let's say, 1/2, 1/2 state, this is isospin 1/2, IZ equals plus 1/2. That implies it's the proton, to one that's a half, and 1, 0. This being the proton, this being the pi 0. That Clebsch-Gordon coefficient is -1 over the square root of 3. If I look up this similar one of the same initial state to 1 minus 1, no, 1 plus 1, sorry, 1/2 minus 1/2. This is the pi plus, this is the neutron. That's minus square root of 2 over 3. You get the relative factors of square root of 2 from the square root of 2's differences in these Clebsch-Gordon coefficients. So using the Wigner-Eckert theorem, you could reproduce this using Clebsch-Gordon coefficients. And do people understand what I'm saying when I say that? I'm quickly going through how you would do it in group theory. Basically, some matrix element would then be some reduced matrix element in the Wigner-Eckert language times the Clebsch-Gordon coefficient. Okay, I don't know if my I haven't developed this notation, but the Clebsch-Gordon coefficients give in a reduced matrix element is how you'd parameterize it using group theory. In the SU2 case, it's not that hard to do some of these calculations, but in a SU3 cases or SU4, it's much easier to do it this way. Another example that is much easier this way, if I had, let's say I had an invariant, the Lagrangian is minus lambda over 4 pi I squared. That's an invariant. You can then write that out. That's minus lambda over 4 times pi 0 squared plus 2 pi plus pi minus quantity squared equals minus lambda over 4 pi 0 to the 4th plus 4 pi 0 squared pi plus pi minus plus 4 pi plus squared pi minus squared. Okay, the matrix elements then can be just read off of this. If I want pi 0, pi 0, L, pi 0, pi 0, well, that's just the first term there. This is just lambda phi to the 4th. this gives me minus 6 lambda, like our usual calculation, 6I lambda, usual calculation. Actually, I don't need di there, sorry. Okay, if I want pi 0, pi minus, pi 0, pi minus, that comes from this term here. This field can create a pi minus, and this field then, this annihilates the pi minus, that one creates a pi minus. So if I read it off of that, I get minus lambda over 4 times 4 times 2. The 2 comes from the fact that there's two ways to employ this, but there's only one way to employ that. One of the pi zeros in pi 0 squared can annihilate the first one and then create the second, or the reverse. Yes?
Why is there no I?
This is just the Lagrangian. When you find the Feynman rules, you write e to the I Lagrangian. So the I is from. So I haven't gotten. Yeah, that's right. This guy would be pi 0, pi 0, pi 0, pi 0. The Feynman rule would be minus 6I lambda. Okay, the I comes from I lambda. I just didn't happen to write down the Feynman rule there. I wrote down the Lagrangian. Okay, now these, and you can clearly write out let's do one more, pi plus, pi minus, Lagrangian pi plus, pi minus. That comes from this last term. There's the factor 4 that cancels that, and now there's two more factors. There's twofold ambiguity here. One of these annihilates one of the pi minus to begin with. One of these annihilates the pi plus to begin with. So there's an extra factor of 4 there, so this is equal to minus 4 lambda. Now, these also could be gotten by group theory factors with Clebschus, but here you're crossing a 1 cross a 1 into a 1 cross a 1, and there's a lot of options there. This gives you the group theory pretty trivially. So we'll take advantage of this and use these little rules that we've developed to write out invariant Lagrangians. Okay. Any questions before I move on? I want to write out 2 examples, and then move on to SUN. Okay. 2 examples. One is in ON scalar theory. This is n real fields phi I is equal to 1 up to n. Okay. From what we've done, we already know that phi I is an ON invariant. So it transforms, phi I goes to Rij, phi j with Rij, Rik equals delta jk. So this generalizes from 2, which we did, or 3. We were doing O3 up to On. And the Lagrangian that you'd write out for such a field would be 1/2 d mu phi I minus some v, which is a function of phi I itself. So v would be typically plus or minus mu squared over 2 phi I minus lambda over 4 phi I to the fourth. So that's how you typically write out an ON theory. The following one I want to write out is the linear sigma model. This actually is your next homework. But I want to write out the notation here so that you're clear about it, because I can only type so much. This was proposed by Gilman and Levy, 1960. But it's a nice toy model. It has an awful lot of stuff in it, and we're going to use it for various lessons. The first lesson is just to get you to do some of these calculations with chirality and with invariances. So let me just write out what it is. So it's like our nucleon example where we talk about a doublet field which will give charges psi n and psi p. There'll be 4 mesons in it, sigma and pi I, which is like pi I and pi 4. You'll always write this with invariances of sigma squared plus pi I dot pi I, which is an 04 invariant. Okay, there's 4 fields there, pi 1, pi 2, pi 3, pi 4, written as the sums of squares. So that has an 04 invariance, just like this ON invariance up there. So there's a rotational symmetry in that piece. So V of sigma squared plus pi squared, the interaction pieces, would be this plus or minus mu squared over 2 sigma squared plus pi squared minus lambda over 4 sigma squared plus pi squared squared. However, the place where it changes is we couple the fermions and the scalars in the following way. We do the Lagrangian is psi bar id slash psi minus g psi bar sigma minus I tau dot pi gamma 5 psi minus this v of sigma. Okay. One of the things to note is that there is no mass term. The mass term would violate the symmetry that we're about to write out. But there is this coupling here. So there is the gamma 5 for the pions. There is no gamma 5 for the sigma. Okay, so you would normally read this thing that sigma is a scalar meson, the pi is a pseudoscalar, etc. Now, the point of the homework is to show that there is an enhanced symmetry. It's not 04. The symmetry is it's an SU2 on the left-handed fields and an SU2 on the right-handed fields. So it's not just a plain old SU2, but it would mean that all those left-handed fields that we talked about can go to some psi prime, which is a transformation on them with L is an SU2 matrix, so it's e to the minus I alpha dot tau, alpha left dot tau. Psi right goes to some psi right prime, is a similar transformation but different. R is also an SU2 matrix, alpha right dot tau. Alpha left and alpha right are not the same. And then the sigma minus I tau dot pi, no gamma 5, goes to sigma prime minus I tau dot pi, which is L sigma minus I tau dot pi R dagger. Okay, so this has this, which will turn out, as you'll show us, amounts to a rotations between these guys. So it's a subset of the O4 rotations, a particular subset of the O4 rotations. All right, so that's what you will show. Anyone have questions about what's the content there? Yeah.
So I'm just trying to remember. So don't you have spontaneous symmetry breaking?
Well, we'll get there. At this stage, it depends a little bit on what you choose for this potential here. If I choose one sign or the other, I get symmetry breaking or not. But the invariance is unchanged. The invariance doesn't depend on that. So for the homework, I don't even spell out what this is. I just say it's a function of sigma squared plus pi squared. Okay? So the proving of this, the reason it's really simple exercise. If you struggle on it, come to talk to me, because it's not supposed to be a struggle. It's supposed to be simple. It's just a little bit of playing with left-handed and right-handed fields, and a little bit of this taking traces that I went through today. So it's just repeating all these things to show these invariances. So it should be simple, and it just sets you up in this compact notation that we're doing. Okay, good. I'm right where I hope to be at this stage. I want to do SUN very quickly, because basically the reason all this notation is useful is that it just generalizes to SUN without any real change. So we're going to take psi is psi 1 to psi n, an n-component object, with invariance with the transformation property psi goes to psi prime equals u psi. U dagger u equals 1, determinant u equals 1. So again, you can factor out the overall U1 phase. You're left with a SUN matrix. So this is written, if we ever need to write it, we write it as e to the minus I alpha dot lambda, where now the dot product means e to the minus I alpha I lambda I, with I running from 1 up to n. There's n minus 1, I'm sorry. There's n minus 1, n squared minus 1. There's, from the counting that we did before, there's n squared minus 1 Hermitian matrices that are traceless. Sometimes we write this as e to the minus I alpha a TA. So T and lambda are the equivalent of doing sigma and tau. Just sometimes you use one, sometimes you use the other. The lambda I are 3 by 3 traceless Hermitian matrices. They satisfy trace lambda I, lambda J is 2 delta ij by convention. That's the convention, just like the Pauli matrices, it's the convention. I mean, yes, it's 2. It's still 2. Yes. Yes, it's not n. So, actually, just to show you why that could work is, if I take lambda I with I equals 1, 2, and 3, are almost always chosen to be the Pauli matrices, zeros everywhere else. So the fact that you embed the Pauli matrices with that same normalization gives you the 2 instead of the n. Yes, that was a stretch. Okay. We don't really need need too much of this, except that my little favorite identity, lambda I A B, lambda I C D is 2 delta A B delta C D minus, and I got that backwards, sorry. Delta A D delta C B minus 1 over n delta A B delta C D. Okay, so the only change there is the 1 over n. Okay, and that preserves the tracelessness of this. If I take it, if I sum over delta AB here, that should be traceless, and that keeps this side traceless. Okay, so the representations. The psi is the goes to U psi is the fundamental. It has n components. The adjoint is lambda dot some vector goes to U lambda dot vector U dagger. So it's again the same development. I would repeat that. If I take traces, so there's n squared minus 1 of those, because there's n squared minus 1 of the lambdas. This would be Vi goes to Rij Vj with Rij being 1/2 trace U tau I U dagger tau j, just like before. Invariants are things like psi bar lambda dot v psi. That's an invariant. If I want vi vi, that's an invariant. That's 1/2 trace lambda dot v lambda dot v. And we'll work on a couple other invariants. You could also have things. If let's say I had I could take 1/2. If I had various invariants. I could take trace lambda dot v1, lambda dot v2, lambda dot v3 if I wanted to. As long as those are all in the adjoint representation, they transform the same way. That could be some triple coupling. We'll see some examples of that, etc. But the advantage of doing this matrix notation is that everything I did for SU2 now can be done for any SUN without any real change in notation. Okay, so let me stop there. That's all my group theory. And next time we come back and we start gauge theory. And this is all the extension section.